Good morning, everyone. I'm Sam. I'm a postdoc at the CFA. I'd like to thank the conference organizers for putting together this conference. It's been great so far. The first iteration of Know Thy Star was actually the very first conference I ever attended as an undergrad. So I'm very grateful for the opportunity to be back, to be back here and give a talk today. So today my talk will be focused on asking the question, what are the ultimate fates of hot Jupiters? The one-sentence answer is, well, they get engulfed by their host stars. Just like any other short-period planet, as the star evolves, it expands, and even Mercury and Venus in our own solar system will get eaten up by our sun as it evolves into a red giant. But for hot Jupiters, as we've already heard, their death may come even earlier than that, and that's because of tidally driven orbital decay. Hot Jupiters are so massive and they orbit so close to their host stars that they raise significant tides on their stars, and because they orbit faster than the spin period of their star, the tides raised in the star tend to result in a backward torque on the planet, and that causes the planet's orbit to shrink, eventually spiraling into the host star. However, many of the details of tidal dissipation inside stars are still poorly understood, and so whether this happens on astrophysically relevant timescales before the star expands into a red giant is still an open question, and one which would benefit from observational constraints. Amazingly, we have actually observed orbital decay in action. WASP-12b is a hot Jupiter with an orbital period of around 26 hours. And by monitoring the times of the planet's transits over many years, it was found that the orbital period is steadily shrinking. And in 2020, building on the work of many people over a decade, we finally obtained the decisive evidence that showed that WASP-12b is indeed spiraling into its star, with a change in orbital period of around 30 milliseconds per year. That means that in just around 3 million years, WASP-12b will be destroyed. More recently, another planet, Kepler 1658b, was also found to be potentially undergoing orbital decay, and there are several ongoing campaigns to monitor the transit times of the most promising hot Jupiters, although right now no other convincing cases have yet been found. Now, even before we obtained the final evidence to clinch the orbital decay scenario for WASP-12b, there was an excellent paper from Jacob Hamer and Kevin Schlafman in 2019 that argued that signatures of tidal decay could already be found in the population statistics of hot Jupiters. And what they found is that hot Jupiters orbit a population of stars that are preferentially young. And their interpretation of this observation is that hot Jupiters experience tidal decay and are destroyed over gigayear timescales. Well, we just heard from Stephen all about how you can use the velocity dispersion of a stellar population to understand the ages and compare ages of different populations. So I won't go into that, I won't repeat that again. But what Hamer and Schlafman found is that the hot Jupiter host star population, which you can see in the yellow line, has a significantly lower velocity dispersion than a comparable sample of field stars, matched with respect to the stellar mass and their height above the galactic plane. This result was followed up by various more recent studies, and you've heard some of the more recent work from Stephen, but here I'm showing one result from Chen et al., who also used kinematic ages, and another by Miyazaki and Masuda, who used isochrone-based ages to find evidence that hot Jupiter occurrence really does decline as a function of stellar age. But these studies were limited in various ways. The Miyazaki and Masuda study used results from the California Legacy Survey, a long-running radial velocity survey, but that sample contains only roughly a dozen hot Jupiters orbiting sun-like stars. And to make this plot on the left, Chen et al. Used the planets discovered by the ground-based transit surveys like HAT and WASP. But that's a very heterogeneous collection of planets, and they had to reconstruct and correct for each survey's biases and selection functions with fairly limited information of what actually went into the selection functions for those surveys. This heterogeneity and incompleteness of the known hot Jupiter population is why we conducted the TESS Grand Unified Hot Jupiter Survey. Hot Jupiters have deep and frequent transits, and so TESS is essentially 100% complete to detecting such planets around even relatively faint stars. And as an all-sky survey, TESS allows us to unify the past 3 decades of exoplanet searches along with new discoveries into a single homogeneous sample with a simple and well-understood selection function. So over the past few years, we carried out follow-up observations of hundreds of hot Jupiter candidates detected by TESS to determine which of them are false positives and which of them are real planets, and then to characterize the host stars and the planets themselves. We've assembled a magnitude-complete sample of roughly 400 transiting hot Jupiters orbiting FGK stars brighter than a Gaia magnitude of 12.5. Of these, around half were previously known from the ground-based transit surveys, and we worked together with many other groups to fill out the rest of this sample. And in particular, I'll highlight the work of Jack Schulte, who's a grad student at MSU, and you can find his poster in the poster hall after this. So the goal of our survey was precisely to answer questions about hot Jupiters at a population level. And because TESS has observed essentially the entire sky, we have a good understanding of the underlying stellar selection function and the stars that were searched to find these 400 transiting hot Jupiters. So we can revisit those earlier studies using this larger and more homogeneous sample. Here I'm showing the distribution of the galactic velocities for the TESS hot Jupiters in orange compared with the stars that were searched to find those planets in blue. And you can see by eye that the hot Jupiter hosts really do have a narrower velocity dispersion than the field stars. But there are other correlations that we need to take into account when comparing the two populations. And the most important one of these is the correlation of stellar metallicity. Giant planet occurrence varies by more than an order of magnitude as the host star metallicity changes. And you can see here that the hot Jupiter hosts have a significantly more metal-rich host star population than the galactic field stars. And this has to be accounted for because as we go out to larger galactic velocities, we incorporate a greater proportion of stars that were born in the galactic thick disk. And those stars are also preferentially metal-poor. And so this means that a metal-rich population of stars should be expected to have a lower velocity dispersion than the field, irrespective of their ages. So to check this, we measured the dependence of hot Jupiter occurrence rates on host star metallicity using that test sample. And then we use this power law relation to generate simulated planet populations with the same metallicity distribution as the observed hot Jupiter sample. The blue histogram shows the results of these simulations where we have computed the velocity dispersion for each synthetic population. And the spread in this blue histogram shows the statistical uncertainty on the velocity dispersion given the small number statistics that we have. So you can see that the metal-rich population of stars really does have a lower velocity dispersion than a population of stars that has a metallicity centered at roughly the solar value. But when we compare that with the actual hot Jupiter host star population, we find that those have a still lower velocity dispersion, with the significance of this result being roughly at a 3 sigma level. We can also measure the completeness-corrected intrinsic occurrence rates of hot Jupiters as a function of galactic velocity. And you can see that hot Jupiters do indeed become intrinsically less common as we go to larger values of the galactic velocity. And you can also model this as simultaneously with the metallicity dependence. And even then, there remains a significant residual trend that cannot be explained purely by that metallicity effect. So these results confirm that stars that host hot Jupiters really do come from are really a kinematically young population. And so one possible interpretation for this is the one that Hamer and Schlafman put forward, that hot Jupiters are destroyed by tidal orbital decay over gigayear timescales. But there's another potential explanation, which is that the formation of hot Jupiters might have been less efficient in the distant past. And so in my remaining time, I'll just briefly mention a few of the steps that we are taking to distinguish these two possibilities. So if we go back to the first 2 known hot Jupiters with apparently decaying orbits, I'll note that the orbital decay timescales for both of these are on the order of a few million years. That's many orders of magnitude shorter than their system ages. And that begs the question of why we are observing them at this special time. One clue comes from the fact that both of these stars are not main sequence stars, but that they are subgiants. They've started their evolution up the subgiant branch. And this is in agreement with some theories for tidal dissipation. For example, in this recent work from Nevin Weinberg et al., where they looked at wave breaking or gravity modes inside stars. They find that stars that are more massive than the sun, they have convective cores while they are on their main sequence, have very weak tidal dissipation during that time. But as the star evolves, the convective core shrinks, and that can lead to drastic drops in the tidal decay timescale by several orders of magnitude. So it is possible that these planets only started having decaying orbits when their stars started evolving up the subgiant branch. So going back to the homogeneous sample of hot Jupiters, I uniformly reanalyzed all of those systems to derive isochrone-based ages, incorporating constraints from Gaia parallaxes, broadband photometry, and the stellar density from the planet transit. And while the resulting ages still have a fairly large uncertainty, I find that if we divide the sample into a population that's either more evolved or less evolved, we find that the more evolved host stars apparently have a deficit of the shortest period hot Jupiters. And that would be in agreement with the very steep dependence of tidal decay rates on the planet's orbital period. I'll stress that this histogram probably overestimates the significance of the results because it doesn't account for the very large uncertainties in the ages that are derived in this way. And we also need to consider the alternative hypothesis that hot Jupiter formation was somehow less efficient in the past. For example, a paper by Tim Hallett and Eve from last year suggested that the high star formation rate and strong radiation field in the past would have limited the timescale over which planets could have formed. And so to address this problem, we've started investigating hot Jupiters that orbit stars that are part of the galactic thick disk. And to do this, I'm working with Victoria Di Tommaso, who is a grad student at the CFA, and you should find her in the poster hall to talk about this because I'm out of time. And so I'll leave you with my conclusion. And I think the upshot of it all is that hot Jupiters really do orbit a kinematically young host star population, and that's independent of that metallicity effect that they have. Thank you.
Thank you. We have questions for Sam. Yep, on the right here.
Hey, Sam, great talk. Kyle Franson, UT Austin. This is all really, really interesting. I'm curious, so you presumably have masses and radii and densities for these hot Jupiters. Have you looked at, potential trends in those parameters, either as a function of the velocity dispersion or kind of inferred ages? And I'm wondering if there's anything interesting there.
Yeah, so I did look at those trends with velocity dispersion. I think the issue is that if you go back to this histogram, like I mentioned earlier, the width of this histogram represents the scatter in the velocity dispersion that you would get if you just randomly drew 400 stars from the galactic population. And so all of the differences that I noticed when I looked at those trends, they're kind of a lot less significant than this result, and so I'm hesitant to show them on stage, but we can chat about it later. Yeah.
Okay, we have time for a few more questions. Yeah, in the back.
Hi, Dan Fabrici, U Chicago and NSF. Could you go to your in-prep results? I think it's a few slides ago about the actual distributions of velocities. I noticed that the hot Jupiter hosts had fewer small velocities. I wonder why.
You mean this plot?
No, when you showed the sample histogram and then the host histogram compared, there we go. So the orange is lower than the blue on the left-hand side. Do you know why?
Yeah, that is a good question. I've not thought about that, but I'll get back to you.
We have time for maybe one more quick question. Yeah, go ahead. Oh, yeah, in the front.
Hey, Sam, really interesting stuff. So have you also looked at the obliquities and if they also, the correcting for metallicity as well?
You mean the obliquities and the velocity dispersion?
Yeah, so the result that hot stars tend to be around, or large obliquities around hot stars are older.
Yeah, I think again, like we're limited by small number statistics there, but there was a paper from Kevin Schlafman and I think also Jacob Hamer, maybe from 2 years ago that looked at that. So I think you should also take a look at that work.
Okay, I think let's thank Sam again. We'll move on to the next talk.